Okay, so as an exercise, let pi be the permutation that maps 1 to 2, 2 to 4, 3 to 6, 4 to 1, 5 to 3, and 6 to 5, where pi is a permutation in the symmetric group on 6 letters. Draw the digraph for the permutation pi. Also write the permutation pi in cyclic notation. And determine whether the permutation pi is even or odd. Okay, so new definition. The dihedral group of order 2n, which is denoted D sub 2n, is the group of symmetries of a regular polygon with n sides the elements of the dihedral group of order 2n consist of n rotation symmetries and n reflection symmetries. Now I need to point out that the dihedral group of order 2n is sometimes denoted D sub n, so be very mindful of which notation is being used when perusing the literature for dihedral groups. So let's look at the simplest regular polygon, which is an equilateral triangle. So for an equilateral triangle with vertices 1, 2, and 3, and center O, let rho be the counterclockwise rotation about the perpendicular line through the center O by 360 degrees divided by 3, or 120 degrees. Then, if we rotate the equilateral triangle 120 degrees counterclockwise, then we have a congruent triangle where the vertex 1 is now occupying the position that the vertex 3 previously occupied, and similarly 3 now occupies the position that 2 had, and 2 occupies the position that 1 previously occupied. And so looking at the vertices, we can consider the rotation rho to be the permutation of the vertices, so that 1 is exchanged with 3, 2 is mapped onto 1, and 3 is mapped onto 2. And so this is in cyclic notation, 1 to 3 to 2 to 1. Now if we apply rho a second time, that is, we rotate the triangle counterclockwise by 120 degrees, then we once again have a congruent triangle where 2 moves to the position that 1 previously held, 1 moves to the position that 3 previously held, and 3 moves to the position that 2 previously held. And so this is a rotation of 120 degrees followed by a rotation of 120 degrees, or we can consider rho squared being the rotation counterclockwise by 240 degrees. And if we look at the permutation of the vertices from the original triangle, 1 is now occupying the place that 2 once had. So 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 1. And so in cyclic notation, this is the permutation 1 to 2 to 3 to 1. And so we can consider the map rho 2, the rotation, followed by a rotation each of 120 degrees counterclockwise, which is equivalent to rotating clockwise by 120 degrees. So if we now rotate again by 120 degrees, the vertices have their original position, so that rho cubed is the identity. So now let mu be the reflection about the line through the center and vertex 1 then 1, the vertex 1 remains fixed, and the vertices 2 and 3 exchange places, so that mu can be considered as the permutation of the vertices that fixes the first vertex and exchanges the vertices 2 and 3. And so this is in cyclic notation, the cycle 2 to 3 to 2, fixing the vertex 1. So notice that if we apply the reflection twice, then the vertices are in their original positions, so that mu squared is the identity. So now let's consider reflections followed by rotations. We'll begin with the triangle with the vertices in the original position. If we rotate, or rather reflect the triangle about the line through the center and the first vertex, then vertex 1 is fixed and vertices 2 and 3 exchange places. And if we now follow this by a rotation counterclockwise by 120 degrees, then the combination of applying the reflection and the rotation is rho times mu, and this can be regarded as the permutation of the vertices that maps 1 to 3, 2 is fixed, and 3 is mapped to 1. And so this is the cycle, 1 to 3 and back to 1, leaving the vertex 2 fixed. So notice that this is equivalent to fixing the second vertex and rotating about, rather reflecting about the line through the origin and vertex 2. So that 1 and 3 exchange places. And so the combination of the reflection followed by a rotation is a reflection symmetry. So if we again begin with the triangle with all the vertices in the original positions, we apply the reflection about the line through the origin and the first vertex. Then 2 and 3 exchange places. Again, if we apply the rotation counterclockwise 120 degrees, this is equivalent to reflecting about the line through the origin and the second vertex. If we now apply a second rotation, then this is the map rho squared times mu, which, regarding it as a permutation of the vertices, we have that 1 exchanges places with the vertex 2, while 3, the vertex 3, is fixed. And so in cyclic notation, this is the cycle 1 to 2 and back to 1. And so applying a reflection followed by 2 rotations is equivalent to reflecting about the line through the center and vertex 3, so that vertices 1 and 2 exchange places. And so this also is a reflection symmetry. And so the dihedral group of order 6 has 3 rotation symmetries, and 3 reflection symmetries. The rotation symmetries are rotation counterclockwise by 120 degrees, rotation counterclockwise by 240 degrees, which is the same as clockwise rotation by 120 degrees, and leaving the elements as they are, or rotation by 360 degrees. The reflection symmetries are reflections about the line through the origin and the vertices, where mu is the reflection about the line through the center rather, and the first vertex. Rho times mu is the reflection about the line through the center and vertex 2, and rho squared times mu is the reflection about the line through the center and the third vertex. And so the dihedral group of order 6 consists of 3 rotations: the identity, rho, rho squared, and 3 reflections: mu, rho times mu, and rho squared times mu, where the identity is the same as 3 consecutive rotations or 2 consecutive reflections. So notice that the dihedral group of order 6 is algebraically the same as the symmetric group on 3 letters, in the sense that we can consider the rotations and reflections as permutations of the vertices, and we'll make the statement algebraically the same as more precise in the next lecture, and we will use the term isomorphic. So in general, the dihedral group of order 2n consists of n rotation symmetries, rho through rho to the power of n, which is the same as the identity, n reflection symmetries, which is mu, rho times mu, through rho to the power of n minus 1 times mu, where rho is the counterclockwise rotation about the perpendicular line through the center O by 360 degrees divided by n, and mu is the reflection about the line through the center and the first vertex.